Okay, good afternoon, everyone. I'm really sorry if you were expecting the other talk, but it has to be cancelled. I'm really happy to have been upgraded from the ICS village to the main stage, which is really nice. Okay, today I'm going to talk about one of my R&D projects. It's called DYODE, that stands for Do Your Own Diode. The idea is very simple. It's to build do-it-yourself, low-cost data diode aimed specifically at the industrial control systems. Okay, just a few words about this project. So it actually wasn't my idea, it was the idea from Ari, which unfortunately is not here today. We worked together doing audits and pen tests on ICS. Now he's a tax exile working at the Big Four in Switzerland. So for myself, my name is Arnaud Soullié. I'm French, as you may hear. I do pen test and research at Wavestone. I especially work on ICS security and Active Directory security. And most of the time, I give workshop explaining to people how to pen test ICS. That's actually what is going on in the ICS village. So I left my colleague doing it to come here. That's enough about the presentation. Are you guys familiar with ICS, with industrial control system? That was a rhetorical question. I'm just going to explain it anyway. So let's take a look at this slide. Industrial control system, very basically, this is the systems that control any plant, any factory, any building automation system. So you will find it everywhere, in every vertical, in the pharmaceutical industry, in the energy sector, transportation, manufacturing, everything. To give you just really a one-on-one vision, this is a very simplified network diagram of what an ICS may look like. On the right side, you will have some sensors and actuators. Those are electrical devices. They perform an action or they give an action, and they are managed using electricity. To manage those devices, we use what we call PLC, Programmable Logic Controller. You have one here from Schneider. You may be far, but you can come afterwards. Basically, this is a small computer with electrical inputs and outputs. So that allows this computer to control the sensors and the actuators. That's the production network. If we go one level up, you will have the supervision network, in which you will have Windows machines most of the time, servers, laptops, workstation, with a specific software that allows you to manage the PLC. So the idea is to centrally manage all the plant, all the factory, or even if we're talking about critical infrastructures, for the energy distribution, for example, you may actually manage the whole country energy distribution from one single point. And most of the time, not to say all the time, this is somehow connected to the corporate network, the wide area network from the company, or the internet. So of course today I'm talking about one solution that may, in specific cases, allow you to secure your ICS. Okay, now we're talking data diodes. Sometimes you will also encounter the term one-way gateway. The idea of a data diode is very simple. It's that the information goes one way and is not able to go backwards. That's really the simplest idea. How do we do that? We do that using the light as a transport medium, contrary to what we do with Ethernet, where most of the time it's copper cable. And we use some very low-level physics properties of the optical components to make sure that the information only flows one way. So for example, in the light-emitting diodes or the photodiodes, you have a PN junction that prevents the electrons from going backwards. So the idea is that the security is backed by physics. I'm not saying that it's hack-proof. I'm just saying that we have a very high level of trust in those specific devices. That's why it seems interesting to me. Okay, I did not invent the concept of the data diode. It has been existing for long years, mainly used in the defense industry. Here you have some example of commercial data diodes. So those are the one I know. I'm sure there are plenty of other brands. I'm just not doing any advertising for those brands. Waterfall, Fox IT, Thales. Only problem, is that those are high performance data diodes, but also very costly. And when I say very costly, it's several dozen of thousands of dollars annually. So it's not easy when you perform an audit to say to your client, you should just install data diode. Okay, why this project? So as mentioned, Ari and me, we worked a lot on ICS assessment, pen test, security audits, and we discovered that the ICS was always somehow connected to the internet, connected to a third party, or connected to the corporate network. So there are a lot of risks because of this connection. Commercial data diode is too costly, so the trade-off is not easy to sell to your client during the wrap-up meeting. Two examples in which we would have recommended a data diode. The first one is for predictive maintenance. So, for example, you have a provider that asks you to send a 100 kilobyte file every 6 hours to his data center. He uses this data to perform some kind of big data shit to, let's say, predict when the hardware is going to fail. That's the whole idea. So as you can see, it's really slow bandwidth. It's not even critical, because if you are not able to perform the predictive maintenance for 2 or 3 days, that's not going to endanger your physical process. Same for cooling units. One of my clients in the pharmaceutical industry had a third party, in order to reduce the cost of the cooling units, wanted to have direct access to the PLC outputs in near real time. So the idea was to connect a third party directly to the PLC. Let me tell you, the security level of PLC is really not satisfactory, and it's not a good idea to allow somebody outside of your network to be able to access that directly. So in those two examples, we really needed a way to secure the connection, but since this connection were not critical, or at least not business critical, it was difficult to sell to the client the fact that he has to invest a lot of money into a data diode. So this work is based on previous work, mainly from Philippe Lagadec, Austin Scott, and Robert Gabriel, who in the past have been able also to, let's say, create the concept of do-it-yourself data diode, but for us it was not satisfactory because it was not easy to reproduce. So what do we wanted? We wanted to have something that is low cost. You can do it yourself using commercial off-the-shelf and open source software with a target cost of about $200 per unit. We just wanted to perform a proof of concept, having an easy to deploy solution, and to share the results. So it's important to say that I'm not selling anything today. It's just an R&D project. It's all open source, and I will be glad if someone gets this idea, think it's nice, and let's say sells it. But I'm not going to do it. I'm a pen tester. That's not my job. Okay, so here I'm going to detail the first version of the data diode that I did not bring along because it's quite big. Here you have the new version. But a bit of history, how did we do that? In order to use light as the transport medium, we wanted to use copper optical converters. So those are like small boxes. On one side you have an Ethernet cable, so copper connection. On the other side you have two optical connections, one for the reception, one for the transmission. The idea is very simple, it's just to plug optical cable from transmission port on one to reception port on the other one. Since you do not plug a cable the other way around, it's not possible to have any kind of data flowing backwards. However, we ran into a little problem. It's the fact that the first copper optical converter does not want to send data because he thinks the link is down. So we actually use a third one, and that is plugged to nothing on the Ethernet side, just to make the first one believe that the link is up. So that's kind of a trick. Another way of doing it is using optical cable that has like a loop, but it's actually more expensive to buy this kind of cable than just to buy another converter. Also, we wanted to use this data diode for TCP protocols, because that's what is used in real life. And so it's not possible to just make a TCP three-way handshake if you have a one-way connection. So that's why we needed what we call counters, which are computers, basically Raspberry Pis, and we have one on one side and one on the other side, and the job is to perform some kind of protocol translation to allow a TCP protocol to flow in a one-way connection. Okay, so this is what the first model of the diode looked like. So you can see it's a nice, in a nice 19-inch rack. We put some screens to be like the big players in the security boxes industry. On the inside, it looks like this. You will find the two Raspberry Pi that I just mentioned. You will find the TP-Link. Those are the copper optical converters. And as you may see, there's only one cable going from one side to the other. So it's quite easy. It was quite fun. It actually displayed the French flag and plays the national anthem when you boot up. Okay, so how did we do that? We wanted to go quickly. As it is an R&D project, the idea is not to invest too much time. So we were looking at existing solution to transfer data on a one-way connection. We stumbled upon UDPcast, which is software available on Linux that was mainly, I think, used for satellite connections. If you know a bit about satellite connection, which I do not, I just understand that the downlink is cheap, but the uplink is very expensive. So people wanted to use satellite connection to just broadcast some data without having to pay for the uplink. So there's a function in UDPcast that allows you to send data through UDP using forward error connection. So that means that if you have any kind of, I would say, difficulty during the transmission of the data, it's possible to detect the error and to correct it, just like when you download some things from a news group. On top of that, we use some Python code to, let's say, develop some features over UDPcast. So the ability to transfer a file, the ability to transfer Modbus data, and the ability to share a screen. And then we tried to improve. We noticed that UDPcast was quite slow. There was a big latency, especially for Modbus transfer, which is small data, but that you need to send at a high frequency. So we just implemented a very naive Python UDP socket implementation to send the data. Okay, now for the first demonstration will be in video, because as mentioned, I did not brought the big diode. Okay, let me see. Okay, just before it starts, the idea here is that on the left side you will have one workstation in the ICS, Industrial Control System. On the other side, you will have a workstation in the corporate network. The idea is that you want to send data from the ICS to the corporate network. First feature is the ability to send a file. So let's see how it works. The way it works is that on the first Raspberry Pi, we have a network share. You just have to drop a file in here. So I'm just going to drop the file. Then the file will disappear once it's copied to the other side. And then the corporate workstation just has to go to another network share, this time on the other Raspberry Pi, and he will get the file. I'm sorry, that's an old joke, but it's not going to run for a very long time. Thanks. So also just wanted to say, this is just like the user view. I'm going to go into the technical details just after that. Okay, so second feature I wanted to highlight is the Modbus transfer. So it was not easy to do with a real PLC in the video. So here on the left side, I just have a PLC simulator. So that's Modbus PAL. And on the right side, I actually have a Modbus command line client that will poll the values every second. So as you can see, a few seconds after I modify the value on the ICS side, you can see them on the workstation from the corporate network. So it's really not real time, but it's 1 to 2 seconds of delay, which is acceptable in most of the use cases I mentioned earlier. Okay, Sorry. And the last feature I wanted to showcase is the ability to share the screen. What's the use case? Let's say in your ICS you need some support, level 3 support, because you have a very deep problem you cannot resolve locally. So you actually call your provider and you are in a conference call with him. He is able to see everything that goes on your screen, but is not able to perform any kind of modification because you want to keep the control on what's going on in your ICS. So the way it works, it's just that there's a small script to be launched on the PC you want to share the screen. And on the corporate network, you just access a website that updates the screenshot twice a second, which gives the illusion of video. It's not going to work for Netflix, but it's sufficient, the quality is sufficient to be able to read what's going on. And if I zoom on the clock, you see there's a 1 to 2 seconds delay. So I think very acceptable for this specific use case. Okay. Okay, so that was the scenario I just demoed. So the data diode is between the supervision network and the corporate network. From a technical point of view, how does it work? So I'm going to detail the 3 transfer workflow, starting with the file transfer. On the left side, again, ICS. On the right side, the corporate network. So first thing, you copy a file into a network share. What's going on in the input corner, so in the first Raspberry Pi, it will take the file name, it will calculate a checksum and send that to the output Raspberry. Then it will send the file, it will calculate the checksum again. If it matches the one you received earlier, you know that the file is the right one, and it will be copied to the network share. And so the computer from the corporate network is able to connect to this network share and get the data. For the Modbus transfer workflow, it's quite the same thing. Actually, on the input Raspberry Pi, we have a Modbus client. Each second, it will poll the real PLC, get the data, serialize it, send it using UDP sockets to the output Raspberry Pi, on which we instantiate a Modbus server, and the values are updated once a second. So what actually goes on is that on the corporate network, instead of connecting to the PLC, you just connect to the Raspberry Pi. And you have the illusion of connecting directly to the PLC. The way it works is quite interesting because since there is no network connection between diode in and diode out, you can actually set the IP address of diode out to the same as the PLC. And that means that you can just replace the Ethernet cable with the diode. There's no need to reconfigure the software. And for us, that was really interesting because let's say people in the ICS, they do not like to change things once it works. The less you touch it, the less it breaks. So that's interesting because you do not have to modify anything from on the PLC or anything on the server side. Last one, the screen sharing workflow. Actually, I was trying to do something with VLC because you may know that, but VLC has a feature to stream some video from your desktop using UDP. Actually, it didn't work that well, but then I, let's say, had a meeting with someone selling commercial data diodes, and I've been able to see a bit how it looks like and how they do it. And so I decided to do something quite similar, which is taking a screenshot twice a second, sending it to the network share, then it goes to the output diode, and here we have an Apache web server that serves an mJPEG file, which is basically new JPEG files being sent twice a second. So actually that's one of the big vendors I mentioned earlier does, or at least it looks like, so I got this idea from seeing a real data diode. It's really easier than streaming video. Okay, since we wanted also to have a simple solution, here is what the configuration file looks like. The first 3 lines are quite useless, name of the configuration, version, date. Then you define the IP and MAC address of both sides, so that means the Raspberry. Why do we have to do that? Because since the connection is only one way, standard mechanism like dynamic ARP will not work, so you have to use static ARP and define the correspondence between the IP and the MAC address. And then for each module that you want to use, you just define the type, for example, a folder, you put the input network share, the output network share, you just specify a unique port to allow multiplexing of data. And then for the PLC, it's quite easy also. You just set the IP address of the PLC and then what kind of data you want to get. For example, here I want to get the register number 0 to 100 and from 400 to 450 and some coils, 0 to 10, 100 to 110. For the screen sharing, it's actually quite easy. It's basically a file share on which you just copy screenshots all the time. So quite easy also. So as you can see, it's not that hard to configure. Okay, so as I mentioned, the target cost was $200. However, if we do the real calculus here, the first version we did was 374 euros, so a bit over budget. So you can actually reduce the cost because the screens are useless, they do not display any kind of useful information. I'm sure you can find a cheaper rack box, because if you take a look, the rack is actually one of the most expensive PCs. So we were satisfied, but not that much, because that's still too much. And we decided we needed to go cheaper. And that's why we built the number 2. But first, one question I really got a lot: why not just cut the cable? When you talk about data diode, a lot of people will come to you and tell you, actually in an Ethernet cable, you have 2 cables for reception, 2 cables for transmission. So if you actually configure it in half duplex mode on each side and you cut the cables, you will have a data diode. Well, that's kind of true. It seems simpler than what we did. However, the biggest problem you have is that it's still not possible to do TCP connection. So you will still need to have on each side a computer in charge of performing some network translation. And also, that may sound very theoretical, but there are some ways to use the reception cable to transmit information. One of the scenarios is, for example, to, let's say, shut down the network interface, then bring it up, and depending on the frequency, you may be able to transmit some information using that scenario. Don't know if that's clear, but since the other Raspberry Pi will be able to know if the interface is up or not, you can use that to transmit information. So it's possible, it's simpler, yes, but also it's not a proper data diode, and we wanted to have something that's like the real deal. Okay, so to reduce the cost, what did we do? We changed the Raspberry Pi by Raspberry Pi Zero, which are about $5 each when you can find one. It's quite difficult to find one. And actually the problem I have today is that the latest version have built-in Wi-Fi. So it's not really ideal to have components with Wi-Fi when you try to perform the data diode, because you have a built-in side channel. So actually at the moment I used Raspberry Pi's version 2, because version 3 also has built-in Wi-Fi. So if you know how to find Raspberry Pi Zero without the Wi-Fi, I'm willing to give you some money to have some. And also, we decided to go for a cheaper solution, replacing the copper optical converters. And that's actually a suggestion from someone when I was giving this talk. He told me about, yes, we use optocouplers to isolate from an electrical point of view 2 parts of an electrical circuit. Could you use that to, let's say, build a data diode? And actually, yes, we can. What is an optocoupler? As you can see here in the diagram, basically it's a light emitting diode on one side, it's a photodiode on the other side, and so it allows you to transmit information through this tiny integrated circuit. It's quite cheap because, let's say the chip is about €2. It has an acceptable bandwidth. Using Raspberry Pi number 2, I was able to get about 20 kilobytes per second, which is not much. That does not allow me to perform screen sharing. It's probably not enough to perform file sharing, but for example, for Modbus data transfer, that's really more than you need. And also for very sensitive environments, you can do your own. For example, if you do not trust the integrated circuits, and you think maybe there's no data, there's no light emitting diode, it's just a cable inside, you can actually build this kind of circuit yourself. It's not that difficult. You just buy the light emitting diode, the photodiode, and you do it yourself. Okay. Let's take a look at the price. Actually, what's quite expensive is the micro USB to Ethernet adapter, if you use a Raspberry Pi Zero. But that allowed us to have a total cost of €80, which is under the $200 that we aimed at, so we were really happy. On the right side, you can see, let's say, a breadboard with all the required components. It's quite easy, and there's two capacitors and one optocoupler. And on the left side, it's a logic analyzer capture, but I don't think you can see it properly. Yeah, well, it's just to measure the time that the information takes to go from one side of the optocoupler to the other one. It's about 10 nanoseconds, something like that. So yes, depending on the, let's say on the optocoupler that you buy, you will have some speed limitation. Okay, so that is what the final prototype looked like. So as you can see, you have two Raspberry Pi Zero on the left, on the right. On the bottom, you have the Ethernet adapters. And on the top, you can see that we have designed a custom PCB to make it look like a bit proper than the breadboard. Very easy. There's just two capacitors, as mentioned, the optocoupler. And so you have all that in the package that is about this size, 15 centimeters per 15 centimeters. So I think that's really acceptable from a size and a cost point of view. As mentioned, this is an R&D project, so we decided that everything should be open source. So I will display the GitHub link later, but the code is open source and the hardware is open source as well. The PCB, you have the netlist and the Gerber files if you want to get the PCB produced. And you also have the STL file for the 3D printing the case, which is quite easy to do. Of course, you have to adjust that. For example, it really depends on the USB Ethernet adapters that you use. So what's online is compatible with the precise model that I use. If you use another brand of USB Ethernet adapter, you may have to tweak the case a bit. Okay, so now since the video demo worked, I'm going to try to perform a real demonstration of the new one. It's probably going to fail. Okay. Just to explain a bit the setup, here I have a PLC, so it's a Schneider PLC. It's connected to some kind of traffic light. This is managed by a SCADA software that you find on the left side of the screen. And on the right side of the screen, I have the same SCADA software, but it's not connected to the PLC. It's actually connected to the output Raspberry Pi. So the idea is that on the left side, it's inside your ICS. So that's your team managing the physical process. And on the right side, it's another VM going through another network adapter. And that can be an external provider to which you want to give view access to the process. So what should happen is that I can actually switch some lights on and off. And yes, with a few seconds of delay, you can see that on the right side, the information is copied. So of course, since I do not want to cheat, I'm going to show you that if here I try to perform an action. Of course, it's not working because it's trying to send data to the PLC, but actually it's sending data to the diode, so it does not go through. Which leads me to an interesting fact. Actually, I can still modify all the values that I want on this side. They're just going to be overwritten with the real ones. But the diode does not protect from everything. It just makes you, with a high level of trust, believe that the information is not going to the physical process. But actually, you can still perform a lot of attacks on the diode. So you can, for example, if you are able to compromise the output Raspberry Pi, you will be able to, on the fly, modify all the data that I send. So that's not what I'm protecting from. I'm protecting from someone performing illegal action on the SES side. So that's why here I can modify the, it seems like I can modify the process, but actually it's going to be overwritten with the real values. And as you can see, the light is still on, even if I turn it off. Okay, that's it for the demonstration. I'm going to switch it off. Okay, so this demonstration was another scenario. Since we have Modbus only, the idea that I just displayed, as mentioned, is to give access to an untrusted third party, maybe an ICS vendor, read access to the values of your PLC. Okay, so now the hard part. I just described everything that the diode does. I'm just going to also talk about what it doesn't do. Is it magical? Will it protect your ICS? And will it make your ICS hack-proof? No. Most of the time, in an ICS, you will need to get some information out, for example, production data that you want to give to a partner or to the corporate network, but also you will need to get some data in, for example, security updates for the software, PDFs that the people working in the factory have to read to perform their action. So you have to be careful, because using a data diode, if you have just the same connection at another network point that is two-way, that doesn't seem right. So it's not for everyone, it's not for all the processes, it's for very specific use cases, and you will not be able to use data diodes everywhere. That's just what I wanted to say with this slide. Also, very, very, very important, the threat modeling. So it's really simplified. What does this project guarantee? Like any other data diode, it just guarantees that no data will go from the output Raspberry to the input one. That's the only thing, period. If you want to have, I would say, a robust solution, you still need to rely on classical logical hardening of the Raspberry Pi. One example, for example, at the moment, SSH is enabled on the output Raspberry Pi, because I need to modify the configuration during the test. If I leave that open with the default credential, as mentioned, someone will get access and modify the code from this diode, and it will be able to send any kind of data to my third party. So denial of service also is a possibility. If someone sends a lot of packets to the Raspberry from the output, I will not be able to get the values. But what I'm sure of is that this denial of service will not propagate to the ICS. So that's really, really important to understand. Okay, I also unfortunately have to talk about the limits of the project. It's quite slow. At the moment, the first version was able to get about 3 megabytes per second when transferring a file. So that's not too bad. However, as mentioned, using the second version with the optocoupler, it's more like 20 kilobytes max. And even worse, if you use the Raspberry Pi 0 instead of a Raspberry Pi 2, it goes down to 3 to 4 kilobytes per second. I've not identified why. Maybe the physical serial line is is slower, I do not know. Other very important thing, when we talk about data diodes, since it was mainly used in the defense sector, people always talk about side channels. So we did not do anything to prevent side channel, because that's not in our, let's say, threat model. We want people to use that to make sure that a standard or a sophisticated attacker will not be able to, let's say, to compromise the process. But we do not take into account the fact that each Raspberry could be modified by a nation-state agency to add some kind of radio frequency capabilities to discuss between the two Raspberry Pis. That's just something that we do not do. We had the project at one time to use like, they have forensic evidence bags in which you put a phone from a suspect, for example, and that acts like a Faraday cage, so preventing any kind of radio frequency emission. So we thought at a moment about putting each Raspberry Pi in one of those bags, but then we decided that just out of the scope of what we want to do. I'm also aware that people have been able to use the GPIO pins from a Raspberry Pi to perform radio communication using frequency modulation. So that's also one of the side channels that is available. So maybe it's a good idea to actually cut the pin heads of the GPIO of the Raspberry if you want to. But then again, I do not think that should be in the threat model. And of course, at the moment, I did not perform a very thorough gateway hardening. So on each side, there might be a possibility of hacking the device. So it's not totally compatible with safety critical environments yet. Roadmap. I'm not going to detail everything, but let's just say the first thing we would want to do to make this product more useful is to add protocols support. So for example, at the moment we do Modbus because it's the most widely used. We also like to have S7, which is the protocol used by Siemens PLC and also very used in our clients. We'd like to add OPC UA also. A lot of stuff. One thing that may be interesting is the link status monitoring. So to have some kind of heartbeat mechanism. So let's say the input of the diode sends each 5 seconds a small data to the output. And so if we do not receive this heartbeat, we know that we have to reboot the device or something like that. Because at the moment, I've not said that, but at the moment, let's say, if you go back to the situation where you copy a file in the network share and it doesn't appear on the other side, you have no way of knowing that. That's the whole purpose of the diode. It cannot send alert because no information can flow the other way around. So at the moment, you just have to do it again until it works. Maybe using some kind of heartbeat mechanism may allow us, I would say, to prevent that. Other project that we have, adding some kind of file integrity checks. So there are several things you can do. For example, validate the extension, the MIME type, stripping all active content using something like exefilter, for example, or maybe even performing signature of the files. Well, we have a lot of ideas and not a lot of time, unfortunately. And last thing is being able to store a log of all the files that we send to have some kind of traceability. But then again, that's really not the priority. Okay, so this is an R&D project. I wanted to share where it's used, and that's not in a lot of places at the moment. One of my clients decided that he liked the idea, but he wanted to do it his way, so he developed a similar solution using Ethernet copper optical converters and .NET code that he developed. So that's the same spirit at this project, but it's not mine because it actually did it before me when I explained the idea. I had some contact with some students from Virginia Space who apparently used this project as part of a summer internship. And I also have one of my clients that is performing at the moment a proof of concept to use this diode to isolate the safety PLCs from the process control. So not a lot of deployments at the moment. I would hope and I would like to have more feedback to try to improve the device, but at the moment I do not have a lot of deployments. Okay, so in conclusion, the demo did not fail. So it works. It's a very simple project, but it works. It's quite cheap, easy to reproduce. You have everything online. It's about $300 for the first version, 80 for the second one. And I would love to have a contribution on the GitHub, because adding more protocols takes some time, but not that much. So if you have a specific need, please feel free to contact me and maybe we can work together to make the product better. The idea for me would really be to let's say to have one standard product that can be used by a lot of people. At the moment, there is no commercial product on this market segment. If you produce security boxes or security appliance, please feel free to steal all the idea and sell that to your clients, because from my perspective as a pen tester, there's a lot of need in this specific market segment, but no product. Okay, so here's the link for the GitHub, and I'm ready for questions.